Alright everybody, in this video let's try to implement the remove functionality on a singly linked list. So what exactly this remove operation does on a singly linked list is basically it is used for removing the node at a given position that is requested by the user. To give a specific definition as part of this remove implementation, what exactly we will do is we will basically take the index from the user and we will basically go to this index and whatever the node that we have at that particular index, and we will simply try to remove that node, and in the end we will simply return that node back to the user as a output. Okay, so that is the ultimate functionality of a remove operation on a singly linked list. Here obviously we are taking the index from the user, right? So obviously there would be two cases. The first case is the valid index and the second case is invalid index. Here if you observe the singly linked list that we have, right, we know the valid values of index on a singly linked list will basically start from 0 and will end at length of the singly linked list minus 1. So for the remove operation, the valid range of the indexes will be from 0 till the length of the linked list minus 1. That means in the singly linked list that we have here, right, the indexes will be at 0, 1, 2, 3, 4 and 5. If user passes any of these indexes, we will be able to delete that node and we will be able to return the value. And one thing that you have to make sure here is whatever the head node and tail node and whatever the length that we are maintaining on the singly linked list, right, we have to make sure that those values are still consistent even after deleting the node from the singly linked list. That is something that that we have to remember. Now let's just try to understand whatever the different cases that can come when we are trying to implement the remove operation on a singly linked list. The very first scenario is basically, since we are taking the index from the user, right, first check would be to check if the index that user is passing is invalid. So that is the first check. When we will say the index is invalid, if the index is less than 0 or if the index that is given by the user is greater than or equal to the length of the linked list. If user passes the index that falls into this range, we will simply return null or none based on our programming language that we are using for implementation. If we are using Java or JavaScript, we will simply return null. If we are using Python based implementation, we will return none. Okay, so that is the first scenario. And the second scenario is obviously a valid index that is given by the user. So in the valid index also, what exactly we will do is we will try to reuse some of the functionalities that we have already implemented. So if you remember the previous implementations that we have done, it right, in those cases, basically when we spoke about those functionalities, specifically when we spoke about the pop functionality and the shift functionality, pop functionality is basically used for deleting the very last node we have in the singly linked list, and the shift operation is basically used for deleting the very first node we have on the singly linked list. So whenever the user is passing the valid index, we can reuse this push and pop shift functionalities. So how will we make use of that is, inside the valid index scenario, as part of the first check, what we will do is, if the index that is given by the user is 0, we will check. If it is 0, right, what exactly we need to do? We need to delete the head node, right? We have to delete this head node. That means whatever the next node that we have inside the singly linked list, that should become the new head of the singly linked list. That's why here this operation is nothing but the shift operation. So we will simply call the shift operation with whatever the index or 0 itself we can pass, because whatever the index that user is passing is 0. In the end, this shift function automatically returns the node that it is deleting, right? And we can return that node itself. Okay, so that is the first scenario. And the second scenario is basically if the index that is passed by the user is equal to the very last we have very last index we have on the singly linked list. That is, if the index is equal to the length of the singly linked list minus 1, and we are anyway maintaining the length in our singly linked list, right? And we will be able to get that length directly, and we will be able to compare it very easily as well. So if it is matching this case, that is nothing but we are trying to delete the very last node we have on the singly linked list. That operation is nothing but pop operation. So we will simply call the pop operation directly. Okay, and I forgot to mention, when we perform the shift operation also, we will not pass any index as an argument, right? Because shift operation itself will basically delete the very first node. So it automatically knows that it has to delete the current head node which is at index 0. So this is a small change. By mistakenly I have written index as a function argument. Okay, now the third scenario in the valid case is basically if the user passes any index from 1 till the last but 1th index. In that case, what we have to do is we have to make sure that we are deleting the node at the index that is given by the user. And now I will explain you what exactly is the algorithm that we follow. Now here, let's assume that the singly linked list that we are using for performing the remove operation contains, let's say, some 5 values or 5 nodes in it. And we have the head node and we have the tail node, and these will have some values like 1, 2, 3, 4, 5 or some other random values they will contain, right? And the indexes will be 0, 1, 2, 3, 4. Now we have already understood when the user passes the index 0 and when the user passes index 4, we have already handled those scenarios. Now our worry is if the user passes an index from 1 to 3, right? Now let's assume that in our implementation the index that is given by the user is 2. So we have to delete this node with the value 3 because it is at index 2. Now to delete this node, what we have to do, we have to make sure that whatever the next pointers that we are keeping track of in each and every node, we have to make sure that we are deleting that. So to do that, what exactly we will do is, first we will get the node that is at whatever the index that is given by the user minus 1th position. So in our case, the index that user has given is 2. So we will go ahead and get the node at the index 1th position because we are trying to get the node at index minus 1th position. Because index minus 1th node will contain the next or the reference of the node that is at the indexed position in the next variable of that particular node, right? So we have to make sure that that node we are updating it to the next of the node that is at indexed position. So what exactly we will do, we will get the node that is at index minus 1th position and we will update the next of that particular node with the next of the node available at indexed position. That means that this node's next will be having the value of or the reference of the node 4. In that way, this node is actually getting deleted. Okay, I hope you understood. What exactly we will do is, first we will go ahead and we will try to get the node that is at index minus 1th position, because in that node we have the reference of the node that is at indexed position. So what we will do, we will simply update that next variable or that next value with the next of the node that is at indexed position. So that is the third scenario where index is greater than 0 and less than length of the singly linked list minus 1. That means that the very last index that we have. Now let's try to perform the pseudocode that we discussed earlier, right? For remove operation, let's try to write the Python based implementation for it. So def, let me just define the function as remove, and the argument that we take is basically the index from which we need to delete the node. Okay, so in the case of remove, we need to delete the node from the linked list. That means the valid range for the nodes are basically from 0 till length of the linked list minus 1. but still whatever the value that user has passed in this index variable could be an invalid value. So as part of the base checks, we will basically check if the index is less than 0 or if this index is greater than or equal to the length of the linked list. In that case, we will not have the nodes in those indexes or positions, so we will simply return null in those cases. Okay, we'll simply return none in those cases since it is Python. Otherwise, whatever the index that I passed, if it is 0, that means I'm trying to delete the existing head node itself. That is nothing but the shift operation. So we will simply reuse the shift operation here. Self dot shift. Oh, sorry. We need to, Python doesn't support curly braces, right? So let me just remove these curly braces. Okay. So when the index is 0, that means we are trying to delete the head node itself. So I'll simply call the shift operation for that we have already implemented. And I will just return whatever the shift operation is returning. If this is not the case, and the third possible case is whatever the index that I am passing could be the index of the tail node, that is the very last index. In that case, we need to remove the tail node itself. That is nothing but the pop operation that we have implemented. So if the index equal to self dot length minus 1, in this case what we will do, we will simply call the pop operation and return whatever the pop operation is going to return. Okay, so we have successfully handled the three cases. One is if the index is invalid value, or if the index is 0, we are trying to delete the head node, which is nothing but the shift operation. If the index is the very last index, that means we are deleting the tail node, so we have reused the pop operation. So apart from any of this, that means anywhere we are trying to delete the node after the head node and before the tail node, we basically need to get the access to the node that is available at the index minus 1th position first. Once we get that, we also need to get the nodes of the index plus 1th position. So once we have these two, we will adjust the next of the index minus 1th position node to the index plus 1th position node, so that we would have deleted the node at the index position. So for that, what I will do is I will define the variable called node. Here I will simply call the self dot get of index minus 1th position. Okay, I've got the node that is at the index minus 1th position. Now let me define one more variable called node to be deleted. It will be the next node of the node that is at index minus 1th position, right? So we can simply do node dot next. Okay, so we have the node to be deleted as well. Along with this, we need the next node also. So for that means let me define a variable called next nodes. The next nodes will be the nodes after the node to be deleted. So node to be deleted dot next. Okay, now all we have to do is we have to make the next of the node that is available at index minus 1th position to the node to be the nodes that are after the index position. So we'll simply do node dot next. We will simply make it as a next nodes. Okay, so and after that anyway we need to return the node to be deleted, right? We don't want to keep track of the next nodes in the return value that we are trying to return. So as part of that node to be deleted dot next, we will simply assign it to none. Okay, and anyway since we have deleted the node here, that means the length of the linked list should decrement by 1. So self dot length equal to self dot length minus 1. Okay, simply return the node to be deleted. Okay, this is how we actually perform the remove operation for all the indexes that user has passed. Okay, now let's just try to call this function and validate the results. Here in the beginning we have the 4 values into the linked list. let me just modify this insert call into remove call, and let's just pass 10 as first index, and it will only need one index. Okay, so since we have only 4 nodes, that means the possible range is from 0 till 3. Since I'm passing 10 here, it should not basically remove anything. Since we are printing, that means traversing the linked list before remove and after remove, right? So the list should remain same. So if I simply just clear it and try to execute Python 3 singly linked list dot py. If you observe the list here, so the before removing and after removing, the values remain the same. As part of the head value printing and tail value printing, you can see they remain same. Okay, similarly, if I try to remove the value at index 0, that means whatever the head that is there right now should be deleted. That means the 10 should be deleted, and the codingpal.arg should become the new head node of the linked list, because the value at index 0 or the tail, sorry, or the head is 10. So if I execute it, see, before deleting, the traversal operation printed all the values. After removal also we printed all the values, but here 10 is not there since we have deleted it. And the codingpal.arg is the head node of the modified linked list, and the tail is still 10.1, and the length of the linked list is 3. Okay, similarly, if you try to perform the remove operation on the last index, that is 3 here, because we have 4 values, right? So the last index is 3. If I execute it, you should see before removing we were able to see all the 4 values. Since the index 3 contains 10.1, we should basically delete this. As a result, the new tail will be with the node with the value true. So after removing, if you see here, and if you see the head and tail values, you will be able to confirm that. Similarly, you can pass any values. Let's say if I pass index 1, that means index 1 contains value codingpal.r. So it should basically delete this node. So if I execute it, you should see before removing we've seen all the values. After removal, 10 true, 10 true, and 10.10 we are able to see. So the head and tail will still remain the same. Okay, so this is how basically we implement the remove operation at a given index by the user in the singly linked list. Okay, I hope you are able to implement it as well as understand it very clearly. If at all, if you have any issues, try to rewatch the videos. After that, go on to the codingpal.org and try to visualize it with the custom input based on your wish, and try to understand it thoroughly. Okay, even if you have any issues, you can definitely reach out. I'll guide you through it. Okay, so here, when will the best case scenario of the remove operation will actually occur? Whenever we are trying to remove the very first node on the singly linked list. That means we have certain number of nodes available on our singly linked list, and we are trying to perform the remove operation of a head node. That means that we are reusing the shift functionality, right? When the user passes the index 0, we are deleting the head node itself. Obviously, we know shift function will automatically take constant amount of time. So in the best case scenario, the time complexity of remove operation is order of 1, which will basically occur when we are trying to delete the head node of a singly linked list. Okay, when will the worst scenario of the time complexity will actually occur? Whenever we are trying to delete the very last node on a singly linked list. That is nothing but we reused pop operation, right? What exactly pop operation had to do? It has to go to last but 1th node, and it has to update the next of last but 1th node to null, right? That's why we have to run a loop for n number of times to reach the last but 1th node. As a result, in the worst case scenario where we are trying to delete the very last node we have on a singly linked list, the time complexity will be order of n, which is nothing but the time complexity of the pop operation. Okay, that is how time complexity and space complexity are calculated in terms of best case and in terms of worst case scenario. Now let's go ahead and let's just try to understand the space complexity of the algorithm that we are writing. Obviously, in the best case, we are reusing the shift operation where we are trying to delete the very first node on a single linked list. In that case also, we simply, we will not do anything. We will simply take one variable like current head, and we will simply update the head node to the next node by using that simple current node or some other temporary variable. As a result, in the best case scenario, the space complexity will be order of 1 only. Okay, so in the worst case scenario, yeah, we will run a loop for n minus 1 number of times to reach the last but 1th node, but we will go to that node with the help of a simple variable called current node. If you remember the pop operation, right, we have taken the help of a current node. Using that current node itself gets updated with the subsequent next nodes as we progress further onto the singly linked list, till we reach a point where we are at the node that is at index minus 1th position. As a result, even though we are running the loop for n number of times, we are reusing a simple single variable like current head or some other temporary variable. Okay, as a result, in the worst case scenario also, the space complexity will still remain order of 1 only in terms of performing the remove operation as well. Okay, so that is the time complexity and space complexity analysis of a remove operation on a singly linked list. Okay.